Right. So, today we will change stream, and today and tomorrow we will talk about a slightly different subject than the one we have been dealing with all these days, namely partial differential equations. Today we will talk a little bit about Lie groups and about the rotation group, specifically the rotation group, its connection to the unitary group, and a little bit of the properties, topological properties of the parameter spaces of these groups. So, this will be just about enough material for today and tomorrow, and let us start off with the material which we already know, talking about the rotation group. We could just as well consider the rotation group in n dimensions. So, very frequently I will talk about n dimensional rotations in n dimensional Euclidean space, or occasionally specialized to 3-dimensional Euclidean space, and point out that there are some very major differences between rotations in an even number of dimensions and an odd number of dimensions. They are very important physically. Now, the notation I use will be that of Cartesian tensors, which I presume everybody knows, the index notation with the summation convention. So, indices like I, j, k, etc. will run from 1 to n in the n dimensional case, or 1 to 3 in the 3-dimensional case. So, let us look at the simplest case, the 3-dimensional rotation. One frequently talks about, we have coordinates xi, I equal to 1, 2, 3, and one knows that under a rotation of the coordinate axes about the origin, keeping the origin fixed, one knows that distances do not change, distances between points do not change at all, and that this rotation is a linear transformation in the sense that xi goes to some xi prime in the new coordinate system, which is a linear combination of the coordinates in the old coordinate system, and it is a homogeneous transformation because the origin does not change. So, the point 0 remains the point 0, the origin remains itself, and it is a linear transformation because it is a linear combination. Each new component is a linear combination of the old components here. Now, the first property we know, and let me give you an example of this thing here. We can write this as a matrix. If I write a position vector r in the form x1, x2, x3, then this matrix R is a 3 by 3 matrix with elements where the matrix itself is orthogonal, as we will see in a minute, because distances are preserved under rotations, and it has got unit determinant if it is a proper rotation. So, let us see what this looks like. An example, for instance, of what R is like would be if you rotate in the xy plane through some angle psi, leaving the z axis untouched, then this will only affect the x and y coordinates, and we can immediately write down from elementary trigonometry what this matrix looks like. It looks like cos psi, sin psi, 0, minus sin psi, cos psi 0, 0, 0, 1. So, that is the matrix which determines what the new coordinates look like, what linear combination they are of the old coordinates here. And since the x3 axis is untouched, all points on it remain where they were originally, you had a 1 here and zeros here, ensuring that only the x and y coordinates get exchanged with each other, get mixed up with each other. Okay. So, that is one example, but more generally, the more general way of writing a rotation is to parameterize this rotation in some suitable form. In this rotation, we fixed the rotation axis to be the z axis, and we said that the rotation is through an angle psi in the xy plane. So, you could do this in general and say there is some direction in space, unit vector n, about which you are going to rotate the coordinate system through some angle psi. So, we will use this notation, and I will write r of n psi to denote the fact that this is the axis of rotation and this is the amount by which the rotation occurs. Okay. Now, of course, this is an artifact of 3 dimensions, because rotation about an axis, the concept of rotating about an axis is peculiar to 3 dimensions. The reason is if you rotate in 2 dimensions, if you are in a plane, the world is a plane, Euclidean plane, then what you are doing is really rotating about the origin. There is no third dimension at all. So, there is no axis of rotation as such. If you rotate it in 4 dimensions, for example, and the coordinates are x1, x2, x3 and x4, you could rotate in the x1, x2 plane, leaving the x3, x4 subspace untouched. Then of course there is no question of any unique axis about which you make your rotation. It is a whole subspace that is left untouched. So the idea that you rotate about an axis, which is the common way we always imagine rotations, is true in 3 dimensions for a very peculiar reason. In 3 dimensions, the dimensionality n equal to 3 and the number of mutually orthogonal independent planes that you can find, okay, one set of planes, independent set of planes, would be in 3 dimensions the x, y, y, z and zx planes. Well, it really means you choose 2 coordinates and that is a plane, 2 coordinates would fix a plane. So the number of planes that you could find is n times n minus 1 over 2, and this is happens to be equal to n for n equal to 3. So the accident that you have 3 planes, mutually orthogonal planes, coincides with the number of axes that you have, is peculiar to 3 dimensions. If you had 2 dimensions, you have 1 plane and no third axis at all. If you had you have 2 axes, the x1, x2 axes, and you have 1 plane. On the other hand, if you had 4 dimensions, you have 6 planes. You have the 1 2, 1 3, 1 4, 2 3, 2 4 and 3 4 planes, but you have only 4 axes, the 1 2 3 4 axis. So you see this accident is what enables you to say I rotate about the z axis. So one should technically say this is a rotation in the xy plane and so on. Of course, these mutually orthogonal planes need not be perpendicular to the coordinate axes. You can choose any set of mutually orthogonal planes, but the number is fixed, it is n times n minus 1 over 2. Okay. So I will use this language loosely occasionally, but one should remember that it is really rotation defined in a plane always. Yeah. Well, if I have n coordinates, a plane is determined by any 2 of them, and these 2 you can choose in n times nc2 ways. So you have that many planes, but then you have n coordinates. So the number of axes that you have in Cartesian coordinate system is n, but the number of planes is nc2, which is not the same as n except when n equal to 3. Okay. So the question of whether can I associate always an axis with a rotation is a tricky one. It is clear that in even dimensional spaces this need not be the case at all. In 2 dimensions there is no third axis at all, so you cannot associate an axis with this rotation about the origin, and in 4 dimensions you have 2 extra axes which may not be touched by the rotation at all. So the question of associating always a unique axis with the rotation is not always the case, not always possible. We will see how in the case of an odd dimensional space you can always do this, but in an even dimensional space this does not necessarily have to be the case. You could have rotation about an axis in a 4 dimensional space, but all I am saying is all rotations do not necessarily have to have a unique axis associated with it. Okay. I mean in 4 dimensions I could rotate about the x1 axis and say here is a rotation, so it will do something to the other coordinates leaving x1 unchanged, but the fact is that you do not always have to do that. There are rotations where you cannot associate a unique axis with the rotation. Okay. All right. Now the next question that arises is, speaking of 3 dimensions, can we say a little more about these rotations? The answer is even in general these rotations form a group, because this combination of 2 rotations, a succession of 2 rotations is again a rotation, as you can easily verify. Every rotation has an inverse which brings you to the identity rotation, which means no transformation at all, the identity transformation, and that is all you need. So there is, under matrix multiplication of these matrices, you can produce the result of a succession of rotations. Okay. So it is clear that there is a correspondence between the set of abstract rotations in n dimensional space and a set of matrices. Okay. And in n dimensional space the matrices would be n by n matrices, that is one way of representing the rotation, and the matrices would be orthogonal. Orthogonality is immediately established. It is not difficult at all, because under a rotation I want xi to be equal to xi prime xi prime. I want this to happen, and now let us write what this implies. Well, xi prime is equal to r ij xj, and the other xi prime is some r I k xk if you like. So this means that xi prime xi prime, this stands for r prime squared because the I is summed over, so it is the sum of the squares of the coordinates here. This is equal to r ij, r I k, let us say, xj xk. So j, k and I, all of them appear twice, and therefore they are dummy indices, they have to be summed over, and this could be written also as equal to r ij r transpose, let us write it the other way. This is equal to r transpose j I r I k xj xk, which is equal to r transpose r, the jkth element, xj xk. On the other hand, that this thing here should be equal to xj xj, because r prime squared should be equal to r squared, but I could also write this as equal to delta jk xj xk, where delta jk is a Kronecker delta. Okay. So this means that r transpose r jk must be equal to delta jk for all j and k, which immediately implies that r transpose r, the jkth element, equal to delta jk, but the Kronecker delta is just the matrix element of the unit matrix. Okay. So this implies that as a matrix, r transpose r equal to the identity matrix, and a matrix whose inverse is equal to its transpose is an orthogonal matrix, as you know. So this means that rotations are orthogonal matrices, and this is, we have arrived at this conclusion by simply imposing the condition that the distance from the origin to any point should be unchanged under the rotation about the origin. That is all we have used. Okay. Now for finite dimensional matrices, r transpose r equal to I also means that r transpose equal to I, because the left inverse is equal to the right inverse in such cases. So it is very easy to establish that. And what does this imply? It says R is an orthogonal matrix by the way, I did not use the fact that you are in 3 dimensions for this. This is true in general, in n dimensions. It is immediately true. And orthogonal matrices, n by n orthogonal matrices form a group. The set of orthogonal matrices forms a group, and it is denoted an element of the orthogonal group, which is denoted by O n. That is the group of n by n orthogonal matrices, and we have restricted ourselves to real matrices, matrices with real entries, real elements. I have not put that in explicitly, otherwise you should put n comma r here to show it is real. Okay. Now this set of matrices has an interesting property. Okay. It is a group, but that group is not a very trivial group. It has some structure to it, and that you can see from the fact that if you take the determinant of this on both sides of r transpose r equal to I, you immediately discover that determinant r squared equal to plus 1. That is the determinant of the unit matrix, and the determinant of r transpose, of course, the same as the determinant of r, because a matrix determinant does not change if you interchange rows and columns. So this implies that determinant r equal to plus 1 or minus 1. 2 possibilities, and they are both included here in this. Now matrices with plus 1 determinant we call proper rotations, because the identity transformation itself has determinant plus 1, and this means that all those matrices which determinant +1, this thing here corresponds to proper rotations. They can actually be constructed continuously by moving continuously from the identity. So you start with the original coordinate system and you want to get to a proper rotation where the coordinates look like this, you can do so by a succession of infinitesimal transformations, each of which has determinant +1. So this property of being connected to the identity is what defines a proper rotation here. On the other hand, there are matrices whose determinant is -1 and they are discontinuous transformations. There is no way of reaching a determinant -1 by continuously starting with the identity and making a succession of transformations continuously. There has to be a discrete transformation somewhere. It would still be orthogonal, but it would not have determinant +1. Now an example in 3 dimensions, for instance, would be this. So if x1 goes to minus x1, but x2 goes to x2 and x3 goes to x3. This corresponds to an R, it is still in the rotation group, but it corresponds to an R whose matrix is -1 in the first diagonal, 1 in the other 2 diagonals and 0 everywhere else, and the determinant is -1. Now of course you will say that this is not really a rotation in the technical sense of the term. Why is it not a rotation? It is a reflection really, it is a reflection about the x2 x3 plane. The x1 axis goes to -x1, right. So a reflection of this kind is still in the rotation group, in the orthogonal group, but it is an improper transformation. So having made this reflection, if you now rotate the coordinate system by a proper rotation, the result is still a determinant -1 transformation, because the determinant of a product of matrices is the product of determinants, right. So you would construct all in an abstract sense, here is the set ON, but it really has 2 disjoint pieces. There is one piece, so one should really write it like this, there is one piece which is determinant +1 and another piece which is determinant -1, and ON has both. The set of matrices is disconnected. There is one set which has determinant -1, one set which has determinant +1, but they both together belong to the rotation group, the orthogonal group. Okay. However, you got to be a little cautious here. Now where do you get the elements of this from? This consists of all proper rotations, things which you can continuously build up from the identity transformation. This thing here consists of all those matrices which you can get by taking a discontinuous transformation like reflection or parity. You could also have had this, you could have had this. This is the parity transformation, R goes to -R. That is called determinant -1 as well. So reflections or parity transformation or any discontinuous transformation which has determinant -1, and you can multiply every element of this set here with one of these transformations and you get an element of this part of the group here. But these things form a group among themselves, and this is called the special orthogonal group. So this is SON, this S stands for determinant +1 or special or unimodular portion, and the product of any 2 of them will still have determinant +1, so they form a group, and there is an identity element in there, so they form a group. On the other hand, this set does not form a group, okay. That is obvious because there is no identity element here, minus the identity matrix is there but not the identity matrix to start with. Or another way of seeing it is, if I multiply 2 of these transformations one following the other, the determinant becomes +1, so it is no longer in this set. But the parameter space of ON therefore is disconnected. There is a piece which is proper that forms a subgroup, and that is the special orthogonal group, and there is a piece which is got only -1 matrices which are proper transformations multiplied by one of these discontinuous transformations. you have to be a little careful here. In an odd dimensional space, the parity transformation is not an improper transformation. It's not. That's very immediately obvious. If you had just two coordinates, x1, x2, so you have x1, x2, inverting this by parity would just do this. This would become x1 prime, x2 prime. So x1 goes to minus x1 prime is minus x1 and x2 prime is minus x2. So it looks like this, but this is a proper transformation because the determinant is got a diagonal matrix with minus 1 on the two elements, and this has got plus 1 as the determinant. On the other hand, you can see that this is attained from this by simply rotating about the origin through pi. So the parity transformation is a proper transformation in an even dimensional space, because the determinant is plus 1. But if I reflected about this axis or this axis, then one of the coordinates changes sign, and then of course it becomes a discontinuous transformation. But in 3 dimensions, which is the most common one we are interested in, parity is an improper transformation. Okay. All right, now having done this, let us ask what is the basic property, what do we do about the fact that these are a group, and how is this group generated, so to speak. And the idea is the following. I would like my target finally is to be able to write down this matrix as a 3 by 3 matrix. I would like to say, you give me an arbitrary axis in space in the original coordinate system, the unit vector, and I rotate through an angle psi from anywhere from 0 to 2 pi, and I want to write the matrix down, the 3 by 3 matrix, just as I wrote it down in the case where you rotated in the xy in the x1 x2 plane. So that is the target, and the way to do this is to observe the following. It is a little algebraic, and the trick is the following. If you looked at R of n was the E3, that was a 3 direction psi. This was a rotation in the x1 x2 plane. This matrix we wrote down by elementary analysis. This is psi 0, and I have been saying that this rotation should be obtainable by a succession of transformations. So if for instance I draw a picture and I say this is x1, this is x2, and then x1 cross x2 is the x3 axis which is coming out of the plane of the board, x3, this form, and I make a rotation in this plane, then it is clear that to get a finite angle I can rotate by a succession of infinitesimal rotations. So let us see what an infinitesimal rotation does to first order. So the same thing tells me R of E3 delta psi, where this is a first order infinitesimal, this thing here is equal to first an I, the unit matrix where I replace all these by 1, to first order cos psi is 1, and I take out the unit matrix, and then plus a matrix which is basically 0, there is a delta psi comes out, and then a 1, a 0, a minus 1, 0, 0, 0, 0, 0. I have replaced sin psi by sin delta psi, which is delta psi itself, to first order, and I pulled out the delta psi, it is a constant, and that is it, that is the matrix. Now for reasons which will become clear in a minute, these quantities here will play the role of what are called generators of these rotations. Repeated action by these matrices will lead to the rotation, and in physics we could leave it as it is, but in physics very often, especially in quantum mechanics, it will turn out that these generators of rotations correspond to physical quantities, namely the components of the angular momentum, and that you would like in physics, in quantum mechanics, to be represented by a Hermitian operator, because we would like to have its eigenvalues real. So to make sure that we do not make a mistake there, let us pull out a factor I in the definition here, and then of course this is minus I, this is I, and 0. That is what an infinitesimal rotation in the xy plane looks like. Let us give this matrix a little name. since it is about the 3 axis. So, let us write this as I1 plus I J3 delta psi. J3 stands for this matrix, and notice it is Hermitian. I pulled out this I to ensure that this matrix is Hermitian. Okay. So, J3 dagger. Now, what we need to ensure, I got to go back and check this out a little bit and you will see where the trick is. We need to ensure that a repeated action of this indeed leads to this finite rotation. Okay. In other words, I am simply saying that if you had a rotation and these were the new axes x1 prime and x2 prime here, and this angle is psi, and I am building it up with a succession of infinitesimal delta psi's with the same axis, about the same axis, then what I am trying to do is to say that I have n such rotations, succession of n rotations, each by an angle delta psi, such that in the limit when n goes to infinity, delta psi goes to 0, this quantity goes to psi. So, I build up this finite rotation by a succession of infinitesimal rotations. Then it immediately implies that R of E3 psi should be equal to repeatedly acting with this matrix. So, it would be equal to OI plus I J3 delta psi raised to the power n, one after the other. But now, loosely speaking, if I replace delta psi by psi over n, and I need to take the limit n tends to infinity, then it is not hard to show that this quantity, you can pretend that this is really a number rather than an operator, but it works just as well as you can verify for matrices. This in fact goes to e to the power I J3 psi. If I had 1 plus x over n to the power n, the limit as n goes to infinity is e to the power x definition. So, it turns out even for operators this is true, and this is e to the I J3 psi. Now, it is not hard for you to do this because J3 is a very interesting matrix, it is a Hermitian matrix. So, it is easy to compute its square, cube and so on, and explicitly show that this thing here reduces to this matrix here. So, that is a little exercise. Show that this matrix, which is I plus ij3 psi plus the whole thing squared, cubed and so on, will in fact reduce to this thing here. Okay. You need the infinite series representation for cos psi and sin psi, that is all you need, and then it will indeed go to this right here. So, first lesson, it looks like if you generate a rotation, finite rotation, by this generator of an infinitesimal rotation, then if you exponentiate it, you end up with a finite rotation. Okay. Now, that is the general lesson. So, these matrices like J3 multiplied by some parameter, when you exponentiate it with an I because you want it to be Hermitian, you end up with the finite element, the finite matrix. Okay. Now, it turns out that these matrices like J3 will obey a certain algebraic relation called a Lie algebra, and this group itself is an example of a Lie group. Namely, it is a group whose elements are parameterized by certain parameters, in this case psi for instance, and these parameters occur in an analytic fashion in the sense of for instance complex variable theory, but more relevantly they appear generally as exponentials, and as you know the exponential of z is a nice entire function, nice analytic function. So, that is a lesson, but now let us see how we can push this a little further. Now, you could ask what happens in 3 dimensions if I rotate about the 1 axis through an angle psi. What would this look like? Well, I need to now write down the infinitesimal variation version of this. So, let us write delta psi here, and this thing here is 1 plus I J1 delta psi in an obvious notation, and the question is what is this J1 equal to? Well, it is clear that all we have done here is instead of the z axis we have chosen the x axis. So in cyclic permutation we can write down what it is going to do. The original about the z axis, the x and y coordinates got mixed up. Now when you rotate about the x axis, the y and z coordinates are going to get mixed up. So it is obvious that this quantity here is going to be, just by copying what I have written down there, it is going to be 0 0 0 0 0 minus I 0 I 0. It's obvious that this is what it's going to look like. Okay. So wherever you had x and y, now you got y and z, and that's it. And what's this fellow going to be? What's R of E2 delta psi going to be? This is going to be I plus I J2 delta psi. And what is this matrix going to be? Now it's the 1 and 3 axes that get mixed up and the 2 remains completely untouched, right. So you're going to have a lot of 0 0 0 0 0 here, and these 4 elements are not going to be 0. The diagonal ones are still going to be 0, but the off diagonal ones, what's going to be here and what's going to be here? Which one is I and which one is minus I?
First row I.
The z will play the role of the original x because you got y, and then in cyclic permutation it's zx, right. So it's clear that this is going to be a minus 1 and that's going to be a plus 1. Okay. So that's J2, and this thing is now complete. I mean, we've got all the 3 generators. So if the group, the number of planes is 3, and there are 3 generators corresponding to infinitesimal rotations in each of these planes. Okay. But the interesting thing is these matrices J1, J2, J3, they form what's called a Lie algebra. In other words, they form a linear vector space among themselves such that the commutator of any 2 of them is again an element of the same set of elements, the same class. So in this case it's not hard to show that the commutator Ji, let's use not I, J k equal to I epsilon j k l j l. Okay. So the commutator of any 2 of these is the third of these matrices in cyclic order. J1, J2 commutator gives you I, J3 and so on. And epsilon j k l is the completely antisymmetric symbol in 3 dimensions. It's equal to plus 1 if j k l are in the even permutation of the natural order 1, 2, 3, minus 1 if it's an odd permutation, and 0 if any 2 indices are equal. Okay. So epsilon j k l has, as it stands, 27 components. Most of them are 0, 21 are 0, and 6 of them are non-zero, 3 of them are plus 1, 3 of them are minus 1. Okay. This is called the Lie algebra. Of SO3. It's denoted by SO3. The convention is to use small letters to denote the Lie algebra of generators, infinitesimal generators corresponding to a Lie group. Okay. The group O3 itself is a Lie group. We are talking about SO3 because we are talking about rotations formed from the identity continuously, and the generators of those rotations, so these guys are the infinitesimal generators. That's a bit of a misnomer. It's technically the generators of infinitesimal transformations. There's nothing infinitesimal about J1, J2, J3 themselves, but I just call them generators. And they form a Lie algebra. These quantities here, the constants in front, they are called the structure constants of the Lie algebra, but we will not worry about that right now, except to see that this defines for you, in a sense, the rotation group in 3 dimensions. Because it means that if you give me all the properties of these J's based on this algebraic relation, then by exponentiation I can actually find the general element of this group. and everything that follows from that. So it is all going to sit in this Lie algebra here each time. Now of course you could ask, what about our target of finding this quantity r for a general axis? What does that look like, and so on? That has a bit of a problem as it stands, because what happens is that the general rotation is specified by an axis n, and the element corresponding to that is this n psi. This is equal to e to the power I j1 n1 plus j2 n2 plus j3 n3. So you first find an infinitesimal transformation about that new axis, which is generated by not j1 j2 j3 but j1 n1 plus j2 n2 plus j3 n3, because n is in some arbitrary direction, and then you must exponentiate it and multiply the whole thing by psi. So you need this quantity, okay, by our prescription that you need to exponentiate the generator, I times the generator times the parameter, okay. But the difficulty is that the j's do not commute with each other, and whenever they do not commute with each other, when two operators a and b do not commute with each other, e to the a plus b is not equal to e to the a times e to the b. It is immediately clear, because e to the a and e to the b on this side would have all powers of a on the left and powers of a on the b on the right, but of course if you square a plus b, it is a squared plus b squared plus ab plus ba, since they do not commute. So this poses a serious problem, and this problem here is at the root of all the physics, all the phenomena that occur in 3 dimensions, because it essentially says that rotations about two different axes do not commute with each other. On the other hand, if you are in a plane, I rotate by an angle psi and subsequently by an angle psi prime. The result is a rotation by an angle psi plus psi prime, since there's both of them are in the same plane, and you could have added them in either order. So the rotation group in 2 dimensions, which is represented by 2 by 2 orthogonal matrices in a plane, this group SO2 is an abelian group, because it is a commutative group. Different elements will commute with each other in either order. So if you rotate, since there is only one point which is kept fixed, the origin, there is no axis here, let me just write r of psi. In this case, r of psi prime is equal to r of psi plus psi prime, which is also equal to r of psi prime r of psi, and the group is said to be commutative or abelian. And that makes a huge simplification. Okay. That is not true in 3 dimensions, because this commutator is not 0. So because of this and the fact that you have a non-trivial algebra, finding this exponential is not as straightforward as it would have been if these operators had commuted with each other. Then the matter would be trivial. But we really need to deal with this separately, the fact that they do not commute. There are identities to do this, but in this particular case it is not very hard to do this, as you will see in a minute, and I am going to write the answer down, but you will see that in general this will be a serious problem. And if you go to n dimensions, then the problem is made much worse, because you have many more generators. You got n times n minus 1 over 2 generators, and the general transformation can be quite non-trivial to write down. Even this will not be a very simple algebraic expression, but we can write this down as follows. So let us see, let us write this j1 n1 plus j2 n2 plus j3 n3 explicitly and see what happens. So the first point is, and this I will establish rigorously, the fact that I have called them j1, j2, j3, and there are 3 of them, suggests to you, should suggest that maybe the components j1, j2, j3 themselves are like a vector, a matrix valued vector, in the sense that each of those quantities is a 3 by 3 matrix, but maybe it is a vector, transforms like a vector, under rotations. Now how do you define a vector in 3 dimensions, say, when you under rotations? How do you define a vector? It is a set of 3 quantities, an ordered triple of quantities, which transform under a rotation exactly in the same way that the coordinates themselves transform, right. So a vector in 3 dimensions, for example, would be a quantity A, and I would write this as A1, A2, A3, and I call this A vector if under a rotation A goes to A prime such that AI prime equal to Rij Aj. If the coordinates transform like xi prime is Rij xj and these quantities, 3 quantities, transform in the same way, then I call it a vector. If it does not change at all, I call it a scalar.
Sir,
If it, yeah?
in general, these quantities should be function of coordinate, right?
Yeah, or constant, we do not care. In general, they could be functions of coordinates, we do not care. But that is my definition of a vector. The elementary high school definition, of course, is vector is a quantity with magnitude and direction, but this is unsatisfactory as a definition, because direction with respect to what? Direction with respect to what? Then you would say with respect to a coordinate frame. Who gives you this frame? Right. So it implies immediately that this statement, when you write an equation like F equal to m times A, Newton's law or something like that, you write it as a vector, nobody specifies what that coordinate system is. So it is obvious, it implies that this law must be valid in all coordinate system of certain class with respect to each other, and it does not matter. Now when will a law be invariant? When it is expressed in terms of quantities whose transformation law is prescribed to you. So the laws are form invariant provided you express them in terms of covariant objects, objects whose transformation law is already encoded in the object itself. That is what a vector is. That is the whole idea behind scalars, vectors, tensors and so on. But anyway, we are talking here about vectors under 3-dimensional rotations, that sort of transformation, and then of course this is the definition of a vector. Now this is not an accident that we wrote it in this form. So it turns out that indeed one can write a vector j equal to j1, j2, j3, and moreover these quantities transform under rotations exactly as the coordinates themselves do. So we are going to write down the finite rotation transformation formula for a vector, and then I will show explicitly that the j's themselves do the same thing. And therefore, I will anticipate that result and say that this is a vector. I will use this notation at least.